Hi, this is Ron Hipschman. Today on Full Spectrum Science, we're going to talk about lasers. It's a very exciting thing for me because I used to work in lasers. I used to work for the Laserium Laser Light Show. I did that for 20 years. Who would have thought that a laser light show would go for 20 years? But let's get right into it. Let's talk about laser light because it's very different from normal light. If you look at it, say, from a light bulb and you turn on that light bulb, it lights up and light waves go out from it in all directions. And what can we say about that light? Well, we can say a few things. First, it's made of many, many colors or wavelengths. Light is moving in all directions, and none of the waves are aligned with any of the other waves. It's called incoherent light. Laser light, on the other hand, looks a little bit different. Laser light might look something like this. Now that, you can see, is very different. That has only one wavelength or color. Also, all of those waves were moving in the same direction, in our case, from left to right. And notice the waves, they're all lined up with each other. The crests align with the crests and the troughs align with the troughs. All of those waves are in phase with each other. So that's what makes laser light very different from any light that's ever been seen before. So laser, we've all heard the word. It's an acronym. It stands for Light Amplification by the Stimulated Emission of Radiation. That's quite a mouthful, and I think that we should take that apart and figure out what the individual pieces are about. Before we do that, let's just talk a little bit about making light. When you make light, you're always talking about atoms. So here I have a picture of an atom. It's an unexcited atom. It has a nucleus in the center made up of protons and neutrons, and the nucleus is surrounded by shells of electrons. In this case, I'm just showing you 3 shells. Now, of course, this is not the proper picture of a real atom, but it works for our purposes as an analogy. The electron can exist in any one of those 3 levels, but not between, and that's because of the laws of quantum mechanics, and there's a definite energy difference between each shell. Now, that energy difference is determined by, again, the laws of quantum mechanics, which we're not going to discuss here. But the electron can only exist at those energy levels. It's like walking up a set of stairs. You can only walk up 1 stair, 2 stairs, 3 stairs. You can't walk up 1.5 stairs. So the atom here is kind of like that. You can only excite it to certain energy levels. How do you excite it? Well, if it's a gas, for instance, atoms in a gas, you can put that gas and stimulate it with an electric charge flowing through it. You can stimulate it by heating it up and causing it to glow, or you can actually shine light of the right frequencies at it. Let's do that in this case. So in this case, I have just an atom with 3 energy levels in it. So let's excite that with light. So I'm going to send in a little pulse of light called a photon, a quantum of light, and that is going to be absorbed by the electron. The electron's going to jump up into an excited state. Now, most atoms, if they're in this state, de-excite instantly. It de-excites because it looks down and it says, oh my God, there's a place I can de-excite to. There's an energy level below me. And so it falls off that cliff and it de-excites and gives up a little pulse of light called, again, a photon. So that's basically how atoms get excited and de-excited. The difference in energy between each energy level determines the color of light given off by the atom. Every set of atoms, every element has its own unique set of colors it gives off, its spectrum, and so every gas that you use in a laser is going to give off a different set of colors. In this case, I just used red as an example. This excitation and de-excitation is what you normally would see in a neon sign or in a fluorescent light. Although a neon sign technically is only the red, like you might see the face over on the right-hand side or the Saturn planet up there. Neon signs only give off red light. The others have mercury in them, which gives off all different kinds of colors. So let's tease apart that laser acronym. Let's start with the last part of it, stimulated emission of radiation. What does that mean? Seems to mean that I have to stimulate something to cause it to give off light. And that's true. Going back to our excited atom, you could think of our excited atom energy states as a hill. And if I put an atom at the top of that, an electron rather, at the top of that hill, it can't stay up there. There's no way for it to stay up on that hill, and it rolls down immediately. In the case of lasers, there are atoms that can get into an excited state, and then they get stuck there. It's another quantum mechanical state. That hill wouldn't look like this. That hill would look more like this, a hill with a little crater on the top. So if I put the electron, or the ball in this case, up there, it's stuck. It can't roll down unless, what? You have to push on it a little bit. And so here, let's apply a little force, and the ball then can de-excite and roll down the hill. So stimulated emission works the same way, where you can excite a bunch of atoms up into an excited state, but they stay there. They're stuck until they are caused or stimulated to emit their radiation. Now, you are actually familiar with this. You probably have some stuff at home that participates in stimulated emission of radiation. Do you have any glow-in-the-dark frisbees or stars that glow in the dark at home? This glow-in-the-dark material, like I have right here, this glow-in-the-dark material is an example of stuff that requires stimulated emission of radiation for it to give up its energy. Let's try that. Let's give it a try. We're going to turn out the lights here, and I'll show you this. This material here is material from our shadow box at the Exploratorium. And if I put it against my chest here and I hold my hand here and I expose it to the light, my hand is casting a shadow. And so if I take my hand away now, my shadow is caught. And again, this phosphorescent material requires stimulated emission of radiation. Pretty cool. I could even write on it with I have an ultraviolet laser. I can write on it too. That's kind of a fun effect too. Going back to our slide of the atom, let's look at stimulated emission from that point of view as well. So here we have an atom, and it's already in the excited state, and it's stuck there because quantum mechanically it's not allowed to de-excite. How do we de-excite it? We have to, again, like the ball on the hill, we have to give it a little push. And this way we're going to give it a little push. Now watch carefully here. A photon of light's going to come in, it's going to disturb it into giving off its energy as another photon of light, and off they go. Let's look at that one more time, because I want you to notice that the resulting photon that's generated goes off in the same direction and the waves are lined up. So stimulated emission of radiation is kind of interesting because the stimulated photon goes off in the same direction and is lined up with the original photon. The waves are coherent. So now that we've covered stimulated emission of radiation, we're going to look at the light amplification part of the laser acronym. Whenever we have amplification, amplification is when you make something, what? Louder if you're talking about sound, brighter if you're talking about light. Amplification just means making something bigger. You probably have an amplifier at home where you take a small signal from your turntable, if you have a turntable, and you make it into a big signal for your speakers. So let's look at it in that sense. Here we have a box that is filled with mouse traps at the bottom of it. Those mouse traps are all set, ready to go. And on each mouse trap, there's a ping pong ball. But those mouse traps cannot snap unless they're what? Stimulated into snapping. A mouse has to come in. Well, we're not going to use a mouse here because that would be cruel. But we are going to drop a ping pong ball into the top of the box. Now, one ping pong ball causes a mouse trap to go off, throws balls into the air, and then those balls are going to cause more mouse traps to go off, and then more and more, and it builds up exponentially until eventually all of the balls are in the air, and we have no unsprung mouse traps below, and the action kind of comes to an end. Well, the same kind of thing has to happen in a laser. In a laser, we need a bunch of atoms that are pre-excited and ready to go, ready to give off their light. In this case, we're going to start with a solid rod of something, maybe ruby, and the ruby has a bunch of chromium atoms in it that will glow, and they'll get excited and get stuck, and then they can be made to glow through stimulated emission. So here we are, we have a rod with a bunch of unexcited atoms in it. Let's excite them by, say, flashing a flash lamp at it. So let's do that. Here we go. Bang, 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 bang. Now all the atoms are excited. And they can't de-excite. Well, if we cause a beam of light, a photon of light to come in through the end of the rod there, it's going to cause stimulated emission to happen. And there we go. Now we have 2 photons. Oh, there's another one, 3 photons. Oh, another one, 4 photons, and out they go. Of course, that left a lot of still excited atoms inside the laser medium here. So it would be nice if we could use them all. And so in a practical laser, you just don't go once through the medium. You actually put mirrors on both sides of the laser medium and bounce the light back and forth. Now these mirrors are kind of special. You'll notice the one on the left says 100% reflective, the one on the right says 98% reflective. And that's because you cannot lose very much light bouncing back and forth. The light only gets brighter in a standard laser by about 2% every time you reflect through the medium. And so if you lose more than 2%, you never get any amplification. So here we have a laser amplifier, and the light bounces back and forth and back and forth, and coming out of it is a beam that gets brighter and brighter as you stimulate more atoms, and eventually you use up all the atoms and it's done. So this is kind of the basis for the laser, a lasing medium and then a lasing cavity that has mirrors at both ends. Now those mirrors, by the way, I said are very special. 100% reflective mirror and a 98% reflective mirror, very difficult to make. Your bathroom mirror at home only reflects about 85% of the light that hits it. To make mirrors like this is high tech. And that's one of the reasons that lasers weren't invented a long, long time ago. This technology didn't exist until the late 50s, early 60s. So let's look at the beginning of laser history. These 2 guys, Arthur Shallow and Charles Townes, were the guys that came up with the idea of a laser, but with microwaves. They were working on radar during World War II and ways to amplify radar waves. And so they worked on an amplifier that used stimulated emission. And that was called a maser, microwave amplification by the stimulated emission of radiation. Arthur Shallow there is shooting an actual pulsed laser into a balloon and popping the inside mouse balloon without popping the outside balloon, because the outside balloon is clear and didn't absorb the laser light, whereas the blue balloon absorbed his laser light and heated up and popped. Their paper, which was published in 1958, was called Infrared and Optical Masers. And this is the paper that actually started the whole revolution. As a matter of fact, Charles Townes was awarded the Nobel Prize in 1964 for the invention of the laser. And here you see him accepting the award from the King of Sweden. Even though they invented the concept of the laser, they didn't actually invent the laser itself. They never built a working laser. It took until 1960 for this guy, Theodore Maiman, at Hughes Aircraft Company in Southern California, to build the first actual working laser. And you can see here he has it. He's holding it in his hand there. It looks like a flash tube surrounding a little pink rod. And that was the very, very first laser, was a ruby laser, and we'll revisit that in just a moment when we talk about the types of lasers. As a matter of fact, let's just move on to the types of lasers right now. Going back to Theodore Maiman, here's a little bit more close-up shot. He's behind his very first laser there. You can see that there's a flash tube, and the flash tube surrounds a rod of ruby, actual ruby. Now, this is not ruby that was mined from the ground, not gem quality ruby. This is grown in the lab, and I'm going to show you that right now. Here is an actual ruby rod from a pulsed ruby laser. The mirrors are actually plated right onto the end of the rod itself. They're not external, so this is the entire laser amplifier right there. Ruby is actually aluminum oxide, which is normally clear, but there are actually impurity atoms in here of chromium. And it's chromium that makes ruby red. And they are the atoms that glow when hit by the external light. And I can cause that to happen with an ultraviolet flashlight. Let me show you there. There, I'm causing the chromium atoms to glow. These ruby rods are not, they're not mined out of the ground. This is not gem quality ruby. As a matter of fact, if you could look at this ruby, it's kind of just barely pink. You don't need a lot of chromium atoms in there for a laser. You just need a few, whereas a ruby gem you'd want a lot of chromium in there to make a deep red color. These are grown in the laboratory in the form of a giant ruby boule that was grown artificially in the lab, and this will also glow red if I light it up with a ultraviolet flashlight. Is that nice? Ooh, ah. So that material is a solid lasing material, ruby. It's a solid material. Here's an example of a couple of gas lasers. These are helium neon gas lasers. Inside of the helium neon laser is a gas tube that looks like this. Inside of this tube is helium and neon gas, so it's called a HeNe laser. And this is stimulated by electricity. You take a high voltage power source, you attach one side of the power supply here, the other side of the power supply here, and it causes the gas inside to glow and excites the atoms. The mirrors are at both ends of the tube, and the light then comes out as a laser beam. Since you can supply electricity continuously, this laser will give off laser light all the time. The ruby laser depended on a flash tube, so it only produced a flash of laser light. This is a continuous laser. Let me show you a better example of that. So this is a helium neon laser, and inside the box here you can see the glass tube. Let me turn it on and cause it to glow. The high voltage power supply across this end and this end is causing the helium and neon gas to glow inside the tube. The mirror is mounted over here and over here. The light's bouncing back and forth between them, and it comes out as a red laser beam. This is the kind of laser that's most known by people, is a red HeNe. But this is not the only color that HeNes come in. Let me show you a different laser. Here's a laser that has inside of it, you can't see the tube unfortunately, but inside here there's a similar tube and an external power supply. I'm going to turn it on, and this laser doesn't produce a red beam, but it produces a green beam. This is a HeNe, but in the industry, these are actually called greenies. Optical scientists do have a sense of humor too. And actually, HeNe lasers also come in yellow and infrared, so different excitation states in the atom can produce different colors of laser light. In laserium, we use a single laser, a krypton laser, that produces all of those colors all at the same time and more. Here is a slide of a krypton laser. That's at the bottom of the slide here. The beam is coming out horizontally, but then it's going through a prism, and the prism is taking the white beam that comes out of a krypton laser and breaking it up into the colors that make up the krypton laser spectrum. In this case, we were able to use blue and green and yellow and red. 4 different colors we were able to use simultaneously during the laserium show. So we've now talked about pulse lasers, continuous gas lasers. So we've had both solid and gas lasers. Lasers can also be liquid. The lasing medium can be liquid as well. And here you can see a dye laser. The dye laser here is just the upper box in the frame. It is being stimulated with another laser. On the bottom part of the frame there, you see a laser that's putting out a green beam of light, and that green beam of light is exciting the atoms inside a liquid dye. And that liquid dye is now glowing. And you can see that there's a red beam that exits the laser up at the top. The cool thing about dye lasers is that you can actually tune them within a limited range. There's a knob on top of the box there which you can tune, and you can tune the laser maybe here from red to yellow in a continuous fashion. Most lasers you cannot change their color. These are really cool because you can change their color a little bit. However, dye lasers are a bit of a pain because in this case it takes another laser to stimulate it, and you're dealing with liquid dye which just gets all over your lab. So we don't have one of those at the Exploratorium. Now, we've had, again, solid, liquid, and gas now. let's go back to the solid laser, the solid state laser specifically. And these are the ones that you're most familiar with in laser pointers. Here, this is a laser diode. This is just a very small package. As a matter of fact, I have one right here in my hand that you can see. You can see how small it is. This is a laser diode. Actually, the laser diode is inside of this package. I'll show you what the laser diode looks like. And it's very small. I mean, here you see it in comparison to a penny. So this is a very, very small package. Inside of that package, there is a little chip. It's actually kind of like an LED. You apply electricity to both sides of the LED, it glows, except this chip inside of here is polished on both ends. The light bounces back and forth and gets amplified and comes out one end of the chip and then comes out of a little window at the end here. Now this is actually pretty small too. This is actually packaged inside one of these, which is inside one of your laser pointers. Now these make all kinds of different colors as well. As a matter of fact, lasers in general have all kinds of different colors associated with them, from the ultraviolet through the visible Roy G. Biv, through the near infrared, the middle infrared, and way out into the far infrared. You can get lasers of any color. Let me show you an example of that, because I have a whole bunch of laser pointers here, so let me show you those. Okay, I have a few diode lasers here that I just wanted to show you, and if I shine, here's a red one for instance, if I shine it now out over the camera, you can't see anything because there's nothing in the air for it to reflect off of. So I'm going to use my smoke machine, my hazer over here, my theater hazer, and it's going to produce a haze in the air. You can probably see it coming across the screen here. Let me blow a little bit of it towards the camera. So that you can actually begin to see the laser beam. Now it has something to reflect off of. Isn't that cool? So that's a nice red laser pointer. Here's a nice green laser beam. This is kind of a special one. This is a cyan laser. It's a greenish blue beam, but you may have trouble seeing that on the camera because sometimes cameras don't show this very well. This is kind of a cyan, greenish blue laser. This one is just on the edge of visibility for human beings. This is kind of an ultraviolet laser. I don't know if you'll be able to see this one. Just barely, I think. This is a blue laser, but this one is not your typical laser pointer. This one is putting out a lot more than a laser pointer. Laser pointers normally put out 5 milliwatts of laser light. Let me turn off the smoke here for a moment. 5 milliwatts of laser light, 5 1,000ths of a watt. So this one here, my blue laser puts out, you actually may even be able to see this beam without the smoke. It's so bright. This one puts out about 1.5 watts of laser light. This is 300 times as powerful as a laser pointer. So you have to be very, very careful. This will blind you in an instant. As a matter of fact, it's so concentrated that you can actually burn things with this laser. Let me show you. So this laser at 1.5 watts, that's a lot of light power. So much so that if I put this on my skin, it would burn me. But I don't want to do that. So let's use a different target. There just happens to be an unsuspecting balloon back there. Let's shine the laser on that balloon and see what happens. Well, that was quick, wasn't it? That was not really a practical application of lasers, although military applications can be used. But let's look at some of the normal applications of lasers. In 1960, lasers were a solution in search of a problem. No one really knew what to do with lasers. And one of the first applications was in eye surgery, because you can operate on the back of the eye with lasers because you can shine the light through the cornea and the lens without cutting open the eye surgically. And so for certain kinds of operations, if you had blood vessels that were leaking on your retina, you could go into the eye with a laser and you could cauterize and seal those leaky blood vessels. Or if you'd been knocked on the head and your retina became detached from the back of your eye and was floating around, you could use a laser to spot weld the retina onto the back of the eye. Now, one of the most common eye operations, and everybody knows about this one, is called LASIK. And in LASIK, they're correcting your vision. If you're nearsighted or farsighted, you can actually correct that out. And the way they do that is they will slice off a little slice of your cornea and flap it off to the side. And then using a laser, they will vaporize very carefully the layer underneath your cornea so that when they put the flap of corneal tissue back onto your eye to heal, when it heals, it'll heal in a shape that's just right and will have corrected your vision. This is revolutionary. If you're a military pilot, you're not allowed to wear glasses, and so you could actually have your vision corrected and have perfect vision, no glasses, and continue with your job. So laser vision was laser vision with LASIK and those kind of things were one of the very first applications. Another kind of medical application, more cosmetic than medical, was tattoo removal. And here you can see someone has a tattoo in the small of their back that they eventually regretted getting. And using a laser, this is an infrared laser, they would shine the infrared laser at the tattoo. Now the tattoo ink would absorb the energy from the laser light and vaporize and leave much less ink below the skin. Here you see them removing the tattoo. That little red dot on her is a Heine laser, or a diode laser, that's just showing them where the laser is going to hit. Now she's removing the tattoo. This is not a painless operation because obviously you're vaporizing ink inside your skin. So this does hurt a little bit, but then again, getting the tattoo hurt as well. So we think these people can probably take the pain involved here. Now, she puts on an ice pack here because, again, it's a little painful. She wants to pre-cool the skin before she vaporizes the ink. Now this tattoo is quite deep, so all the ink is not removed, and so she's going to have to go back for another treatment. Now there you see she's putting the laser on her skin and it's not affecting her at all. The infrared light from the laser is not absorbed by the skin, so she doesn't feel that at all. And there we go, complete tattoo removal. She'll have to go back and get another treatment to get the rest of the ink taken out eventually after this heals. It's going to take a little while to heal because it's a little kind of like a burn. Another interesting application is one of these right here. This is also an infrared laser, and this is for hair removal. Now, obviously, I don't need this. This was made by a company called Tria, and this one, you just put it on your skin like this, and you click on the trigger, and it will remove the hair and hopefully damage the follicle a little bit as well so the hair doesn't grow back. Now this is not painless either. This would feel like taking a rubber band and snapping it against your skin. So a little bit of pain is involved there, and this only covers a little tiny spot as well. So it takes a long time to remove a lot of hair, and again, you'd have to do more than one treatment with this. Theradome made this helmet here. Let me show you, I have one. This is the Theradome hair growth helmet, and this helmet here has inside of it 80 lasers. And the idea here was you put this on your head and you'll hear her say, treatment resumed. And this is shining 80 lasers on my head, and it's supposedly going to stimulate hair growth. I've read the scientific papers on this, and I don't believe it. Well, if it worked, I'd probably be using one, wouldn't I? An application of lasers that is more industrial is in cutting lasers. Here you see a large industrial cutting laser. This is very powerful. These lasers are in the range of thousands of watts. My powerful handheld laser was a 1 watt. These are thousands of watts, and they can cut through 1/2 inch of solid steel. You can see some of the pieces left over sitting up against the wall there in that slide. Very accurate way of cutting steel, very accurate way of cutting anything, really. We actually use these laser cutters at the Exploratorium. We have a few of them here. Here, you see a laser cutter that this is running at 3 times normal speed, and I'm just cutting cardboard here. And you can see there's a little laser cutting through, and it's cutting out, looks like letters from a piece of cardboard. A little bit of flame escapes there, but not too much. There's a very accurate way of cutting things within thousandths of an inch. And so there you go. You can see I cut the word laser out of a piece of cardboard. Very accurate way of doing things. Here's another industrial application. This one here is using a laser, and that's coming out of that little black box on the left-hand side of the slide, and it's spot welding pieces of metal together. This is part of a car frame, so this was a test for the car industry to see whether or not this was practical or not. Again, these lasers are in the hundreds or thousands of watts, and serious laser, folks. I just love this application on a robot arm. Having a laser on a robot arm, it doesn't get much better than that. Another application, which I think is kind of, well, almost silly, is if you are interested in buying distressed denim, here is a tool that the industry can use to distress your denim without actually having to have somebody actually distress them. Here, the laser is scanning back and forth across this and writing a pattern of distress on this pair of jeans. It'll turn it around now once it finishes that side. There we go. And it's got to now distress the back side. So you don't have to actually use your jeans. You can just stylishly have a pair of jeans that's been pre-distressed. Kind of a silly application, actually. A more practical application is in fiber optics. Here you see just a rod of plexiglass. A green laser is coming into the left-hand side of the rod here, and it's bouncing back and forth inside the rod. And this is how fiber optics transmit light. They keep the light inside the fiber by bouncing it back and forth. These are all fiber optics. They're pieces of plastic fiber optic, and here the base has a light bulb in it. And if I shine the light bulb into the base of all the fibers right here, the light comes out the end. And if you put this just on the table, then it kind of spreads out in a nice spray. That's kind of a silly use of fiber optics, but kind of fun anyway. Another practical application of fiber optics might be in your home sound system. You have a DVD or a Blu-ray player, and that puts out 8 channels of sound, 7.1 sound. And how do you get 7 channels of sound into your receiver without 7 cables? You just have to use one of these, a Toslink cable. This is a fiber optic cable. If I shine light in one end, I have a flashlight here. If I shine light into this end, you can see light coming out of the other end. And what they'll do on your Blu-ray player is they'll shine light in here, they'll blink it on and off, 1s and 0s, and digitally they'll send the sound from one end of the cable into your receiver at the other end, where your receiver will translate those 1s and 0s back into sound and distribute it among all of your stereo speakers. The communications industry also uses fiber optics. All your voice for your telephone, all your internet data goes over fiber optics that look like this. These are fiber optic data cables, and they're very thin. This cable here, the actual cable is the diameter of a human hair inside of here, only like 30 microns across. So these can be, this glass is so clear inside of here, you can have fiber optic cables that are kilometers long. It's amazing that light will actually go through kilometers of this cable. If you have a microscope and you don't want to bring a hot light source near your microscope, you can have the light source separated. Here is a long fiber optic cable bundle. This is a whole bunch of fiber optics all in one bundled together, and this will transmit the light. Again, I'm going to use my flashlight here from one end to the other. So you can have a hot light over far away from the microscope, but the light that comes out the end of the fiber optic is cool. because only the light is transmitted, not the infrared radiation. Another really interesting use of lasers is in making three-dimensional photographs, or holograms, in a practice called holography. We used to carry around on our person's credit cards that had holograms on them. That's become less and less used now. They used to think that these holograms were impossible to reproduce, and therefore making a copy of a credit card would be very difficult, a counterfeit, but turns out they're not that difficult to make. So that has fallen out of favor. But we have a hologram, a real hologram here at the Exploratorium that's titled Lucy in a Tin Hat. And here I'm just taking a video of it, and I'm moving my camera side to side in front of the hologram, and you can see here that you can see Lucy from different sides depending on what perspective I'm taking with my camera. Her entire image is inside the hologram from every perspective. So you can look up and look down, you can look under her hat, you can look over her hat, you can look to the left or right of her hat and get all those perspectives. They're all contained in the same photograph or hologram. In construction, lasers are used to help lay out buildings, and in farming to make sure that farm fields are tilted correctly so the irrigation works. And that works with a device on the left-hand side there. Inside there, there's a laser, and that laser is spinning around in a horizontal plane, defining a flat plane. It's spinning around very fast. And so you can use that and measure above or below that and make, for instance, in construction, like you see on the right-hand side of that photograph, you can make a perfectly flat floor that's perfectly level. Or if you're in farming, you know how to make something perfectly tilted as well, a field, because otherwise irrigation doesn't work. You have to have the field tilted just a little bit so the water runs down. For instance, here, they're installing a pipe, and they have a laser down at the lower left-hand side of that pipe, and it's shining up along the pipe, and they can lay the pipe so that it's straight right along the laser beam and that it's tilted properly. Sewage pipes, for instance, have to be tilted just at the right angle, otherwise the sewage won't run down them. So this is a way to run pipes perfectly straight and at the right tilt. A much bigger example was laying the BART tube across the bay. Here you see a section of the BART tube, and this would be mounted on a barge. They had a laser that ran from the ferry building across the bay to the Port of Oakland, where the BART tube was supposed to exit, and they would float the barges out underneath the laser beam, and they would go out to the position that they needed to be in, and they would lower this section of BART tube down into the bay, bolt it to the sections that were already there, pile rocks on top, because once you filled it with air, it wants to float. And this way, they got the BART tube as an absolutely straight tube without any curves from one point to the other, all lined up with lasers. And this was an early use of lasers, too. You've also seen in supermarkets and even here at the Exploratorium store, a laser scanner that is used to scan the barcode off of products. That barcode is called a Universal Product Code, or a UPC, and as the laser scans across it, it falls on black and white lines, which either reflect or don't reflect the laser light, and that's turned into ones and zeros, which are seen by the laser scanner and is translated back into the ones and zeros and the product code so you can check out quickly. Another case where you see reflected light turned into ones and zeros is on this. Everyone remember this? We used to listen to music with these things. They're called CDs, and some people may even watch television programs off of DVDs or Blu-rays. How do these work? Well, on the surface, if we magnify it very, very highly, you'd see pits and grooves. This is a very highly mirrored surface. Those pits are burned into the surface of the CD with a higher power laser. And then when you put it into your player, a lower power laser is used to scan across those things. The highly reflective surface would reflect the laser. The pits would not. It would disperse the laser. And so again, we have ones and zeros, bright and dark, and those are turned back into music or video or both. And you now have, again, a digital picture medium. Incidentally, CDs are read with infrared lasers. DVDs are read with red lasers, and Blu-rays, you'll never guess. Yes, blue, actually violet lasers. So they really should be called a violet ray, but that didn't work marketing-wise. What else can we use lasers for? Well, one of my favorite uses of lasers is to measure distance. And that you can actually go out and buy at Home Depot for $50. It's truly amazing. This device here, a laser tape measure, has a couple of very simple components. There's a laser that sends out a beam and a lens in front of a photocell. How does this work? Well, again, here we have the photocell and the little laser diode. Let's actually show the real device here. This will send out a beam of laser light that will reflect off of a wall or something and come back through the lens and focus on the photocell. Now, what we really need to know is if we can measure how long that takes to happen, how long it takes for the beam to go out and the time it takes to go back. And we know the speed of light, which is 186,282 miles per second. If we know those two factors, we can figure out the distance, because the distance is only the speed times the time. And so using a simple device, we can measure distances very accurately. Let's give that a try, because I have one of those devices right here. Say we wanted to measure the distance to the asteroid Bennu, which is just behind me here. Well, I can take my trusty laser tape measure, and I can shine the laser on Bennu and press the button. And then I can see that Bennu is at a distance here of 2.647 meters from me. That's a lot closer than Bennu actually is. So here you see a car that is festooned with laser distance measuring sensors. Let me give you a close-up of that. These cylindrical devices you see there are called LiDAR. That's like radar, which measures distance with microwaves. These measure distance with light, hence LiDAR. Here's what the device actually looks like. This is a specific one manufactured by one of the gorillas in the industry, Velodyne. And here's yet a different one. This will actually send out a series of beams and measure the distance to all those beams simultaneously, and it spins around at least 10 times a second, and it can build up a point cloud. It's measuring the distance to a bunch of stuff all at once, building up a three-dimensional picture of the scene outside the car. Here is a movie that was made from the point cloud, a 3D rendering. So the car is moving along the street. It can see all the cars. It can see the moving cars. It can see bicyclists. It can see people walking across the street. And this will allow the car itself to sense people and things and not run over or into other objects. I suspect we'll be seeing self-driving autonomous vehicles within the next 5 years. At least I hope so. I hope that the car I own right now is the last car I own. I just want to be able to go to my phone and say, pick me up and drop me off. Very cool. The Apollo astronauts left 3 reflectors on the moon, and those reflectors are made up of a bunch of prisms. One of them's right here in the Lego model. And using a reflector, you can measure the distance to the moon with lasers very, very accurately, plus or minus about a centimeter. That's truly amazing. Let's see how they did that. Here you see on the left-hand side one of those laser lunar retroreflector arrays. On the right-hand side you see an observatory on Earth shooting a laser at the moon to try and reflect off of that array. That array is made up of a whole bunch of prisms. Those prisms are called retroreflecting prisms. They're corner cube prisms. Those corner cube prisms are designed so that a light ray that comes into them reflects off the corner at the bottom and comes right back in the exact direction that it came from. So it reflects back to the source of the light. I happen to have one of those lunar retroreflective corner cubes. Well, not an actual one. I bought this one. Here is a corner cube prism. It's a circular at the top, but on the bottom, I don't know if you can see it down here, but this is just a corner cube, 3 flat planes 90 degrees to each other like the corner of a cube. Now when light comes into this, it reflects back in the exact direction that it came from. And I can demonstrate that using some smoke and a laser. If I shine light into the retroreflector, the beam coming down here's the beam coming back. This is the beam coming down, this is the beam coming back. There are a couple of reflected rays right here that are being reflected off the front surface of the glass. Those don't count. So here's the incoming ray and the outgoing ray right here, back parallel to the incoming ray. Pretty cool. Another interesting use of lasers is in astronomy to cause stars to detwinkle. We are at the bottom of an ocean of air. We have to look up at stars through that ocean of air. That causes that ocean is moving all the time, the air is moving around, and that causes the images of stars viewed at high magnification in telescopes to move around. And if you're doing long exposures, that kind of spreads the things around. It makes it harder to take very accurate photographs and spectrographs. And so we'd like to be able to calm that motion. One way to do that, to know how the air is moving, is to make an artificial star up in the sky. To do that, an observatory will cast a laser out of the dome into the sky, and in the upper atmosphere, that beam will excite sodium atoms in the atmosphere, so it's a yellow laser. And those excited sodium atoms will act as an artificial star. And by receiving the light from that artificial star, they can tell how the sky, how the atmosphere is moving around. And at the telescope, they have a flexible mirror that can undo all of the motion of the atmosphere and the star and can give you much better pictures. These optical systems are called adaptive optics, and you can't do it without the laser from the observatory. Here's another view taken with a drone. You don't want to do this one for real because you don't want to get those lasers in your eye. And this one is at the Paranal Observatory high in the Atacama Desert in Chile. Here's a movie of it actually. Here you'll see the lasers coming out of the dome and following objects in the sky, and they can then adapt to the atmospheric motion and get much more focused and high-resolution photographs and spectrographs. At the Lawrence Livermore National Laboratories, they're doing a really exciting experiment with lasers. It's called the National Ignition Facility. You can see at the end of the arrow there, that building is the size of 3 football fields, or about the size of the Exploratorium. Inside of that building, there are 192 extremely large pulsed lasers. Those lasers are used to try and collapse a pellet of fuel. Here you see the pellet of fuel. This is smaller than a BB that's filled with hydrogen fuel, hydrogen in the form of deuterium and tritium, 2 isotopes of hydrogen. And that fuel pellet is placed in the middle of a target chamber. Here you see the target chamber. The 192 lasers come in through those portholes in the side. The technicians are working here to set things up, but they'll have to be out of there by the time the lasers go off because, well, there's a vacuum inside that sphere too, so they wouldn't have a chance inside there besides the 192 lasers coming in. Those 192 lasers come in, hit the pellet all simultaneously, collapse it, and heat it to the temperature of 10 million degrees, the same as inside the sun, maybe even a little hotter. There, they're trying to fuse the hydrogen into helium. The idea here is to produce more energy out than the lasers are putting in, and therefore use this as a way of producing energy. This facility is also used for research in high-density physics and also for stockpile maintenance for our nuclear stockpile. One less violent use of lasers is in frightening birds. A laser that's been expanded into a somewhat large spot is just scanned around near some birds out in the field. This scanning laser will scare the birds. This is a problem for farmers. Birds can eat up to 30% of a farmer's crop. So if you can keep the birds scared and keep them away from your crop, this will really increase your yield. And these starlings are now they're gonna murmurate. They flock in these beautiful formations, and I could just watch bird murmurations for hours. We actually have an exhibit here that shows bird murmurations or simulations thereof. You carry around a distance measuring laser in your pocket if you have an iPhone. The later iPhones have in them a dot projector up at the top of the phone there that projects a series of dots all over your face, and those are used to measure the geometry of your face. This is used for the face recognition or to unlock the phone, having the phone know that you are you. A very quick way of unlocking your phone is to identify you using these lasers. My favorite use of lasers is, of course, in entertainment. Laserium, we used lasers reflected off of mirrors to write patterns onto in our case, a planetarium dome. Those devices look something like this. There's a little shaft that comes out of the top of this scanner, and it can move left and right or clockwise and counterclockwise, and we attach a mirror to this. We use 2 of these at right angles to each other as a set of laser scanners right here. Let me show you that more diagrammatically. There's 2 mirrors. One mirror moves the beam up and down. The other mirror moves the beam left and right. The beam will come up and hit the up-down mirror. That will reflect the beam up and down. It'll then reflect to the left and right mirror, and from there it reflects onto the screen, and we can draw anything. So I want to show you now a piece that was done by a fellow named Christopher Short, a quick laser piece, or just a part of that piece, and just give you an idea of the possibilities of laser entertainment. Hope you enjoyed Full Spectrum Science Lasers. We hope that you'll come back at some future point for more in-person Full Spectrum Science. Hey,